Welcome to today's class. I'm glad to have you here. Today I want us to look at the concept of energy quantization. Now, by energy quantization, we mean that the energy of an electron is always released in quantum. But before we move into this topic proper, let us take a quick review of what an atom looks like. Now, for the study of an atom, we know that yes, an atom is the smallest of an element which can always take part in a chemical reaction. Now, for an atom has two parts, which is the heavy part, which is the nucleus, and then we'll have a lighter one, which is the electron. Okay, so we have these two parts in an atom. Now, the study of an atom, because of the nature of an atom, a lot of models came up in order to describe what an atom looks like. Now, we can take a view like a model like Thomson's model, where he imagines an atom to be a homogeneous sphere. Where he imagines an atom to be a homogeneous sphere of a positive charge. Here, this is a nucleus. Now, according to Thomson, he said that inside this homogeneous sphere of positive atom, we have negative electrons embedded. We have negative electrons embedded. And of course, when negative and positive interact, everything collapses. So because of that, his own model, Thomson's model, was discarded. Now, to give us clue on what an atom looked like, other scientists came up, scientists like Rutherford, where he did his own experiments, even though he failed to give a certain explanation. Because of that, his own too was discarded. But let us quickly look at what his own review is all about. Now, on his own, he also said yes, an atom looks like this. An atom has a positive nucleus. Now, this positive nucleus, that electrons spiral around the nucleus in their orbits. So, since electrons spiral around, of course, during spiraling, if here is the nucleus, which is a positive charge, now here is an electron which is negatively charged. And then, if we can still find an electron here, because of that spiraling nature, intermolecular force of attraction will take place. Now, so this is the electron, here is the nucleus. Now, because of the intermolecular force of attraction, negative and positive, this one, of course, this is a heavy core, will always drag this one to its center. And when that happens, the entire system collapses. Now, because of that, his own model was discarded because of his inadequacies in giving a detailed explanation to his experimental observation. Now, his students came up, which is the Bohr. Now, Bohr came up with his own idea. Now, according to Bohr did not carry out fresh experiment. He rather gave a detailed explanation to all those areas that his master Rutherford could not do. Now, on his own part, he maintained this, but now said that an atom can as well be like this, where this is the nucleus. Now, he now said, instead of spiraling around it, he now said, let each of these orbits be different orbits or electron shells, where we can always find electron at each of these. And then he assigned energy to these shells. So assuming if an electron is somewhere here. Let's say E1. Now, this electron, because here it possesses energy, now it can acquire energy, more energy through excitation. Because of course, you know that excitation is just the process of increasing the energy of an electron, maybe through inelastic collision or by heating. So, if this acquires energy, it can now move out of this energy level, maybe to another one, let's say E3 here. Now, because these allowed energy levels are unstable, it will soon jump back, it will soon come back. Now, when it is somewhere here, it can stay there for a moment, and if it gives out its energy in form of light, then it loses that energy. And if it loses that energy, it can now return back. It can now return back. So if it returns back, then this is exactly what an atom we see today look like. Now that will take us to this energy level diagram, because this is an expanded form of what Bohr did. So in other words, these are energy levels. This is the ground state, and of course the ground state, meaning that if this is the ground state, somewhere here is the nucleus. That means this is the lowest energy. The lowest energy level. Electron cannot go beyond this. And then at this stage, electrons are most stable here. These ones are most stable. Whereas this one, as you now move up, the energy increases upwards negatively. Just as you can see here, it increases upward. So he assigned different numbers. So where these quantum numbers, n is quantum number, which can represent 1, 2, 3, 4, 5, as the case may be, integer. Now, if an electron is found somewhere here, that electron, if it acquires energy through excitation, depending on the energy, it can take it up to this place. If it takes it to this place, because all these ones are unstable, only this one is stable, so it will not last long here. So as long as it possesses that energy, it will remain there. So the moment it loses that energy by giving out light, it will jump down. Now, jumping down, not all jumps are to the ground state. It can jump from here to this place, from the E4 to E2, and remain here. And of course, when it gets to this E2, it can still remain here until it acquires another energy to take it up until it loses that energy. If it loses that energy, it can still come down, or it can still come to this place. However, so if it's assuming the loss, it loses energy and jumps from E4 to E2. Now, we can now find the energy loss. Therefore, energy of an electron can be given as energy of an electron. Energy of electron is given as E is equal to negative R all over n squared, where n is a quantum number corresponding to each of the levels, where R is a constant. Now, since R is a constant, now we have a negative sign here. This negative sign implies that yes, you must do some work in order to knock off an electron from any of these energy levels. You must do some work. So because of that, we have this as the formula for the energy of an electron. Now, let us also consider if an electron jumps from one allowed energy level to another, it loses energy. Therefore, energy loss, or energy of one quantum of radiation, energy of one quantum of radiation, energy of one quantum of radiation E, or you can say delta E. Let me say delta E. Delta E is equal to En minus En is where it is jumping from to the ground, let's say E naught. But for the case of this one will be E4 minus E2 at this point. So we put all those values. Now, each of these energy levels have their numbers. This one, minus 13.6, minus 10.4 electron volts, minus 5.5 electron volts, as the case may be. However, for calculation sake or for exam sake, these numbers can be assigned arbitrarily. So if it is assigned arbitrarily, please use the numbers given to you in the exam. Now, back to what I was saying. So if the electron jumps to any level, it can still come back. However, if it enters here, assuming it enters there, that is a continuum. At this point, it will be ionized at this point. So it will no longer come down. Or in fact, once it enters the continuum, it will not try to come back again. Okay. Now, we can also, so since we say that energy loss is equal to En minus this, which is equal to 1 quantum of radiation is HF. Therefore, we can say delta E is equal to HF. Or we can say delta E is equal to HC all over lambda, where H is the Planck constant. H is the Planck constant, and because Planck constant, it has a value. The value is 6.6 times 10 to the power minus 34 joules seconds. That is the value of Planck constant. Now, F is the frequency of radiation measured in hertz. C is the speed of light or speed of electromagnetic wave. Most times is given, in fact, C is speed of light, which is 3 times 10 raised to the power. C is 3 times 10 raised to the power 8 meters per second. Now, the lambda here is the wavelength of the radiation, wavelength of that light. Okay, we have said also before now that delta E is the energy. Now, assuming you want to calculate energy at this level, energy of this level, energy of a certain level will now give us, assuming you want to find energy of level 3. That means level 3, that means n is 3 there. All you need to do is say energy all over n squared. Energy all over n. If n is 2, you say 2 squared. Of course, you will be given the energy level. So if you are given the energy level and given the quantum number, you can always find the energy of a specific level using this equation. Okay, we have this one, we have this, and we have this. So, depending on the parameters given to you, each of these equations are all valid. So, we have this one as an equation. We also have this as an equation, and we have this. All these equations in boxes. So let us solve 1 or 2 problems using these equations. Okay, question says, calculate the energy of the 3rd level. Calculate the energy of the 3rd level of an atom. If the ground state energy is minus 24 eV. If the ground state level is minus 24 electron volt, and we are demanded to get the energy of the 3rd level. Therefore, we now have that n is equal to 3. So energy of the 3rd level, we can always use that equation there. So energy of the third level will give us E all over n squared. So since n is 3, we now have the energy of the ground state energy was given to the minus 24 eV all over n squared. N is 3. 3 squared will give us minus 24 all over 9. 24 divided by 9. From our calculator, we have that the whole thing is 2.7 electron volts. Okay, so that is the answer for that. Now we take the next question. The next question says, in a model of the hydrogen atom, the energy levels. Sorry. Okay, we take it again. In a model of the hydrogen atom, the energy levels Wn are given by the following equation. The energy levels Wn are given by the following equation. W is equal to minus R all over n squared. Where n is an integer, R is a constant. Determine the energy released in the transition from n equals 3 to n equals 2. N equals 3 from n3 to n equals 2. So we are demanded here to find the energy released. So here they have said that this is the equation, and W is given as this. Now the energy released in moving from, let's say, n3 to n2. Now, having given us energy, if you look at this, that equation, W, E was replaced with W. So, we now have that energy released, so solution. In order to solve that problem, we can have, okay. So energy released in the process is Wn, and Wn is equal to W3 from the third level to minus that, the second level. Now W3 is equal to, we'll take W3 first and take W2 first, and then at the end of the day we subtract. So W3 from third level will now have minus R all over here. We have 3 here, 3 squared, which will give us minus R all over 9. Okay, that is our W3. Now, energy released at the second level when it has moved from N3 to N2. So we will still use this same equation given to us, substitute 2 here. We will now have minus R all over 2 squared, which will give us minus R all over 4. Now, having expressed W3 and W2, we will now come back to this equation. Therefore, similarly, we have Wn is equal to W3 minus W2. Now, W3, we'll put it first. W3 is minus 9, minus R all over 9, minus W2. W2 is minus R over 4. So, which will give us, if we open this bracket, we now have minus R over 9 plus R over 4. And of course, the only thing we will do, we will add these two. Adding these two, we'll take the LCM. LCM of 9 and 4 is 36. 9 and 4. 9 and 4 is 36. So we now have that our Wn is equal to, remember this is Wn, which is this, is equal to LCM is 36. 9 times 36, sorry, 9 divided by 36 will give us 4. 4 times minus r will give us minus 4r. You put your plus there. 4 into 36 will give us 9r. So we now have Wn is equal to minus 4r plus 9r will give us 5r all over 36. And this is the energy release in jumping from the N2, from N3 to N2. Okay, now let us take another problem. Now this one says, question says, an electron makes a transition from minus 3.4 eV energy level to minus 13.6 energy level. So from minus 3.4 EV to minus 13.6 electron volts. Calculate 1. The value of the loss of energy due to the transition in joules. Second one, frequency of emitted radiation. And here we are given that 1 EV is 1.6 times 10 to the power minus 19 joules. And then we are also given that H is 6.6 times 10 to the power minus 34 joules seconds. These are all hints. Okay, now if this problem is given to us, the first question says loss of energy loss. And of course, energy loss is delta E equals EM minus E naught. So from where it is falling from to where it landed. So we now have that our En is minus 3.4 electron volts, while E naught is minus 13.6 electron volts. So we now have that the first one, energy loss in that transition, which is delta E. And delta E is En minus E naught, which will give us minus 3.4 minus EO. E naught is minus 13.6 all electron volts, which will give us minus 3.4. Open this bracket, we have a positive sign there, 13.6, which will give us minus 3.4 plus 13.6. At the end of the day, it will give us that our energy is 10.2 electron volts. This should have been the final answer. But because the question says in joules, here, from the hints given to us, they gave us 1 electron volt. All we need to do is to multiply this value with 1 electron volt. Therefore, after that, the energy is equal to 10.2 times 1 electron volt, 1.6 times 10 to the power minus 19, which will give us that delta E is, this is 16.32 times 10 raised to the power minus 19. Therefore, if you put this in standard form, we now have that delta E is equal to 1.632 times 10 raised to the power minus 18 joules. Okay, so this is the energy loss in joules, while this one is the energy loss in electron volts. Now we'll take the second question. The second aspect of the question says frequency emitted during the radiation, or frequency of emitted radiation. Now the frequency of emitted radiation, remember we have a delta E is equal to HF. So we haven't gotten this. H was given to us, and then we can now get F. And I'm getting F. F will give us so we'll recall for the second question. Recall that delta E is HF. Now we have F is delta E all over H, which will give us delta E, because this is they said in joules, we use this instead of the former one. 1.632 times 10 raised to the power minus 18 divided by H. H is 6.6 times 10 raised to the power minus 34. Now we will still continue. So we have, please be mindful of these index numbers. Anytime you are dealing with a high index number, be mindful. So we now have that 1.632 times 10 raised to the power minus 6, minus 18, please. So this minus 18, I want to send this one up. If we send this minus 34 up, the sign, once the process up, changes to plus, it becomes plus 34. All over, the remaining one now is 6.6. So we now say 1.632 divided by 6.6 will give us that F is 0.247 times 10 raised to the power. Now minus 18 plus 34 will give us positive 16. Therefore, F is equal to 2.47 times 10 raised to the power. If this process, this one reduces to 15 hertz. So this is our frequency of radiation. Okay, we'll still take another diagram here. The diagram above illustrates the energy levels of an electron in an atom. If an excited electron moves from N2 to N1, calculate 1, the frequency, 2, wavelength of the emitted radiation, and these constants are given to us. Now the first question, the frequency of the emitted radiation. Of course, you know that since we are solving for the first one, frequency, there is no relationship. So all we need to do is to first get the energy loss, because that a certain electron moving from this to this, it's some electrons some energy were lost. So we now say the first thing, the energy loss, which will give us energy loss, which is delta E is En minus E naught, which will give us En, where it's coming from, which is minus 2 electron volt to where it ended, 12. So which will give us delta E is minus 2 minus 12, all electron volts, which will give us the energy loss is minus 2 plus 12, which will give us 10 electron volts. Remember, they gave us the value of 1 electron. Since we are given the value of 1 electron, they will now say that the energy loss is 10 times 1.6 times 10 to the power minus 19, which will give us 16 times 10 to the power minus 19. Therefore, energy there is 1.6 times 10 raised to the power minus 18 joules. So that is the energy. Now from here now we can proceed to get the value of our frequency. So we now have the frequency. Since it's not given, we now say recall that delta E is HF. From here we can now find the frequency. Frequency is delta E all over H, which will give us 1.6 times 10 to the power minus 18 all over H. 6.6 times 10 to the power minus 34. So which will give us 1.6 divided by 6.6. It will give us 0.24 times 10 raised to the power. Now, minus 18, send this one up, it will give us plus 34. So which will give us 0.24 times 10 raised to the power minus 18 plus 34 will give us 16. So either we'll have this, or we can say 2.4 times 10 raised to the power 15 hertz. Either you have this or you have this, but the one that is in standard form is this. Okay, now we'll take the second question, wavelengths of emitted radiation. Now for the wavelength of the emitted radiation, we use set number 2. We'll say recall that delta E is HF and it is hc all over lambda, where c is the speed of light. So we now have this. So delta E is hc over lambda. Make lambda the subject. Lambda will now give us hc all over delta E. So at this point, we substitute. The value for h was given to the 6.6 times 10 raised to the power minus 34 times c, 3 times 10 raised to the power 8 all over delta E. Delta E, we got our delta E to be 1.6. So 1.6 times 10 raised to the power minus 18. So at this point now, we employ our calculator. So when we now employ our calculator, we have 6.6 times 3. Times 3 will give us, we have 6.6 times 3 times 10 raised to the power minus 34 plus 8 all over. Now I want to send this one up at the same time, plus 18 all over 1.6, which will now give us 6.6 times 3 divided by 1.6 will give us 12.375 times 10 raised to the power. Now you now say minus 34 plus 8 plus 18 will give us minus 8. Therefore, the wavelength is given as 1.24 by approximation here, times 10 raised to the power minus 7 meters. Okay, that is the final answer. Okay. This is where we'll draw the lesson to an end today. Please join me in our next lesson where we'll be discussing photoelectric effects. If this lesson was helpful to you, please give it a thumbs up, turn on your notification button, and then share this video to your friends. Thank you very much.